So to follow that discussion, the basic idea is that big O can be useful whenever we have an inexact quantity. A lot of times where that emerges is in error calculations. So maybe the most significant term in an expression, right? And you're pretty certain about it. But then there's some stuff that that's much smaller that changes a little bit. How do I represent that mathematically? Well, I represent it with big O, right? So I have something like n squared plus O of n. So I know for sure that my n squared bit, right, my most significant term, that is exactly right. But then I know that I have some linear stuff that maybe can change, right? That's sort of my error. So big O is giving me essentially a limit on the amount of error in an expression. So this is actually what they use in things like physics, where you maybe have a measurement or you have an equation, right? And there's that stuff there at the end, right? The least significant terms, right? Where really maybe you were sloppy, maybe you didn't bother to calculate it, maybe your measurements don't have that level of precision. But you can't just completely throw it away. You want to still represent that there is some unknown value, right, in your equation. They do that using big O. So a lot of times you have expressions where there's a big O tailing it just to kind of curfew, right, the amount of error that occurs in this equation. Right, and so once you've kind of encapsulated all of your error in some sort of formula behind a big O, then you can do the algebra, assuming you follow the proper rules, right, and you can compute some final result, right, and you'll end up figuring out what is the error at the end of the day. So you can look here at this expression at the very bottom, right, and so I have here this summation of k squared plus O of k. Let me circle that really quick. So this is what I'm talking about here. And so you can maybe think about our discussion of recurrences and be like, oh, hey, maybe that's something where I want to try and find a closed loop formula for that. And you can actually do that. I put here, magic happens, because it really is a little bit of magic. It'll take you some time to do this. And then what you get at the end, right, is this 1/3 n to the third plus O of n squared. So in this case, right, we're doing some algebra, and the O term, right, is staying in there, because that's representing somehow the error that's accumulated through us doing stuff, right? Here, right, this is a decent answer, right, because we can see that most significant term, right, that n cubed, right, that I know exactly. The only doubt I have, right, after having done all this algebra to find the closed loop formula, that's just n squared level of error at the end of the day. So that's nice, right? I can kind of encapsulate, what I don't know, right? And so they use that, right, a lot. Like I said, in physics is the example I know. I imagine the other sciences use it as well, just as a way basically to represent error or imprecise values within calculations, right, that you otherwise want to keep exact. So just another usage of big O. Maybe you'll see it someday, maybe you won't. It's still cool stuff to know.